Okay, so a little bit of a slow to start right now. I'm doing stuff very last minute, but I want to welcome everyone, all 0 viewers currently, onto the stream. It appears I've also interrupted Shadow Mask movie night, which is very unfortunate because I too enjoy Return of the Jedi. However, tonight is Friday night and the first Friday of September, and it is now past time for me to announce the SEGA Saturn 28th Anniversary Game Competition. So, if all of you would be so kind as to join me on emeraldnova.com, you will be able to find the new link for the 20th Anniversary Game Competition. Now there you will find the contest rules, link to the contest thread on the SEGA Extreme Discord. I believe the discussion thread should be updated. Well, if you can't find it, it'll update soon enough. I think the SEGA Extreme server might just be a touch slow. I can see it on one, not the other. Unfortunate. Anyway, so let's go over the contest details. It is very similar to last year. The music is just slightly distracting enough for me not to be able to go over this. Let's try something else. Nope. Okay, cool. I'll take it. So, contest rules. Very similar to last year. The same categories. I've rearranged the prize pool a little bit. For those of you new to the competition, you will have the next 4 months to essentially work on or continue working on a game or a utility related to the SEGA Saturn. Now, the 3 categories are original game, that is either something that is substantially built from the ground up by you, hacks, patches, and translations, which is essentially taking an existing game that is effectively complete and enhancing it or altering it in such a way that does not constitute generating an entirely new game. Now, you will often see ports of existing games in original games, and that is because those are complete engine rewrites, generally, and constitute a degree of work that warrants them to be in original games as opposed to a hack, patch, or translation. Utilities are generally useful things related to the Saturn: save game editors, extractors, development tools, etc., etc. Those have warranted their own category as of last year, and the interest has not shrunk since then, so they will continue to get the associated awards and prize money and recognition that they deserve. Now, in order to qualify for submitting your entry, it needs to be substantially done in terms of the year 2022. That is, if it is a pre-existing project or game, you need to list what was done in this year in order for the judges to judge the delta or the change or the progression that has been made for this year, the 20th anniversary of the SEGA Saturn. Now, you can go onto the competition thread, and let's see if it's updated yet. Yes, there we go. And the competition thread is where judges can discuss their thoughts on the game and post their scores when the competition time comes, or the judgment time comes. This due date is incorrect, and I need to change that. That's what happens when you do things last minute. Eeny, meeny, miny, you. Sorry, I'm just having to very quickly change the due date on the thread to match that on the website. And hopefully they'll be reflected in the next few minutes or what have you. So by Because we are starting this announcement later than normal, and normally I try to get it done on the 1st of September, no matter what day it is, unfortunately work got in the way, along with my lack of preparation and some last-minute changes to the judge lineup. So we are announcing it today on the 2nd. Thus, I have given until midnight UTC, which is 7 p.m. on America's East Coast, on January 3rd. To turn in, and now judges, to facilitate their schedules, have an enhanced judgment time. They have a full month until February 3rd to submit their scores. February 2nd, nearly a full month. I will announce the scores on a stream on February 3rd, and of course, if a judge gives me his scores within like the last 15 minutes of me going live on February 3rd, I will end up just including those anyway. But I'm hoping the judges will give me at least some time to tabulate stuff, because it's all manual entry. These are scored basically on a point system. Every judge gives their ranks. The ranks are points. You add up the points from all the judgment ranks that you get from every judge, and the lowest scores win. Thus, with 9 judges, a perfect score would, in theory, be 9 points in your category. As you get lower and lower in ranks, second place gets you 2 instead of 1, etc., etc. The whole thing explains itself once the scores start coming in, and the judge is already familiar with the scoring system. What you have to worry about is making the best entry you can within the time limit allotted. Those people that can score high enough to... I need to work on the wording here. Anyone that scores high enough to receive a cash prize is also entitled to a 3D print. I have not mailed out last year's 3D prints yet because the demand was very low, and I essentially just kind of dragged my feet to get it out the door. So I will try to expedite the 3D prints this year and send out last year's and this year's simultaneously. Now, that's it, guys. Via Millennium Shane has generously offered, again, to 3D print the prizes, and he has print files ready for some common things that Saturn enthusiasts may want. Game case repair hinges for the large crystal cases that the Saturn is famous for breaking. Battery door replacements, controller stand, which I have myself and I've actually found quite useful. A display logo, which is just a nice thing to have sitting around. And an ODE tray insert, which is essentially almost required if you're going to have an ODE like the Fenrir, the Rhea, or the Phoebe. Now, going over the prize pool, we have a little bit of rollover. I have to confirm with Xenos whether or not Blue Skies' prize money will be inserted into this table as well. But as it stands, without minus the estimated shipping costs, the last year's prize money... Actually, scratch that, because last year's prize money needs to be adjusted upward because of last year's estimated shipping costs not being met. So this is actually $70 higher than it was last year. Or $70 higher than you're seeing. Yes. So if you go through the table, you have my annual contribution. We have Garrett donated $40 very early in the year, and I've only included it now because it was after last year's competition deadline. The 5th place Original Games prize money was donated back by Slinga. Bulk Slash's first prize money was donated back by Danthrax. Second place, Hexpatch Translation was donated back by Murder of Crows. So that's all on the table already. I need to add in the 70 from last year's estimated shipping costs not being met, so this number is higher than it currently appears already. And you can donate to enhance the prize pool yourself by clicking this handy little donate button, which takes you to PayPal. It says what the money is for. It'll donate to me. In all likelihood, I believe it'll take a nominal fee of like 3.2% or something like that. So keep that in mind, and whatever I receive after the fee will go into the table, and you will be credited as contributing to this year's competition, just as last year's competition, you can see all the contributions from donations then, from people such as Jason Fischetti, Chan Win, Amber Dean, Raymond Maloney, etc., etc., etc. So, I cannot promise you any form of spiritual experience from this unless you decide to pull in several all-nighters induced by some form of chemical assistance. That is on you. I can tell you that it does happen. I can't guarantee it or encourage doing so. For the prize pool, Because of the massive amount of entries we had last year, I've rearranged it so the top prizes may not be as impressive as they were, but there are more prizes to go around. I try to get around, assuming that we get the same number of entries as last year, about half of the entrants should be able to get some sort of prize money. Some of them are smaller than others. So far, with the prize pot being 260, again, remember that's 70 on top of that because last year's shipping costs were not met. You'll get 15% for top prize in original games, decreasing down by 8 ranks to 3%. So the top 8 prizes for original games get not only a cash prize, but are entitled to a 3D print of their choice. Hacks, patches, and translations, the top 5 entries will get prize money, with the top prize being 12% of the total pot. For utilities, the top 3 entries will receive prize money, 10% going to the first place winner. Now, the judges this year are going to look very similar with 2 additions. Cervero is coming back. David Jimenez is coming back. Film Cow himself, Jason Steele, is back again. Genovi Reviews is back. Pandemonium is back. Rev Quixo is coming in to take over for Johannes Vetz, who I was not able to get a hold of this year. I'm not certain what's going on, but again, as a incumbent judge, he is entitled to come back on to judge if he would choose to do so. At this point, I do not know if he is interested or available, so I had to replace him. And so Rev Quixo, if that is how you pronounce that, probably not. It looks a little bit French to me. The longtime member of the community for Sega Extreme, hosted an old website that is now defunct but available on Video Game Rebirth, is a developer on the Terra and Onion mode, and is a contributor to the Redump archival set. Saturn Dave is back. Saturn Memories, for those of you who were in the community for the last couple of years, may remember him. He's not quite as active as he used to be, but he does have Facebook page is no longer active, a YouTube page with lots and lots of Saturn gameplay videos, and he is also the administrator of the Sega Net Discord, which is a great place to connect if you want to play some online Dreamcast games. It also has a little bit of a game development scene going on there, though obviously not quite as big as Sega Extreme. And of course, Traino Co, another Shiro Bro, is back. So that is our full slot of 9 judges for the Supreme Court of Saturn. And that is everything that I can go over at this time for the 28th annual game, or 28th anniversary game competition for the Sega Saturn. Again, if you have an entry that you want to submit for judgment, put it into the contest thread over here. There we go. Due date is updated properly. And if you just want to discuss the competition or any of the entries, you can go over to the discussion thread that is linked in the competition thread. Now that we're done going over that, I will go ahead and try to clip that and push it onto YouTube as soon as practical, probably in the next 3 days or so. And in the meantime, I will try to continue with my SGL catch-up. So unless there's any questions from the audience over on Twitch, I will move on. Gotta close out. I was doing last-minute edits. Okay. So, when we last left off, let us see, what were we doing? We were going through the SGL tutorial. So I gotta go into my game development folder here. And open up the documentation for SGL Developers Manual Tutorial. Alright, let's get that over now. Now, if I recall correctly, the last tutorial I did was, what, chapter 7 or so? So let's see where we were at. Let's get our environment back up and running. There we go. Let's see. If I recall correctly, we weren't on controller input. We were on something to do with 3D. I was talking about if the camera problem on the alternative draw command setup. Come on, where are you? Scrolling all the way up. Jeez. There we go. We got polygons. Nope, 7. We're still on 7. There we go. So we were talking about cameras, I believe. And this was example 7.2. And I was playing around with 7.2. Let's see if I can compile and run. Ah, dang it. Lyrics on stream. You know the rules, PSL. Episode 3? That's not even part of episode 3. There we go. Oh, AM2. I didn't notice that you were AM2 from your name, AM2. I was very confused, but it's nice to know that you are indeed AM2. Welcome to the stream, AM2. You are a little bit late for the competition announcement, but you can always roll back the stream to see what I had to talk about. Anyway, I got my USB controller right over here, so not that I'd use it for this part of the tutorial, but let's go ahead and take a look. Dang it! Why is it every time I use this thing, I always end up having to remap the controls? This is not quite what I remember. Maybe it wasn't 7.2. Maybe it was 7.4? I know I was playing with the camera somehow. Oh, something happened. Oh, yeah, thanks for the follow, M2. Okay, you know what? This is gonna bother me if I don't fix this. Up, down, left, right, start. A, B, C, X, Y, Z, left shoulder, right shoulder. Okay, you know what? Maybe I actually finished chapter 7. Okay, let's clean up after myself so I don't junk up my Google Drive folder. No. 7.6. I bet you 7.6 is what I was playing with last time. Gouraud? No. Did we talk about Gouraud last time? I don't know if we talked about Gouraud last time. No, we definitely didn't talk about Gouraud last time, because I don't remember this. You know what? For my own sanity, I feel like I'm gaslighting myself somehow. Let's look at 6.3. There we go. I don't know why it's spinning, but whatever. So the point I was proving last time with this is that I'm specifically looking almost directly down. I have the camera position at minus 30.0001 and the camera target at minus 30, with the other parameters being more or less identical, except the Y is changing from a distance of 150 to minus 10. That's a distance of 160 units in engine. Now, you saw how clear the picture was looking top down at the tops of those cubes, which are whatchamacallits. Okay, they're cubes. They have pink tops. Yeah, okay, describe them perfectly there. I'm looking at a slightly obtuse or slightly acute angle, just the teeniest bit off normal. What happens when I go to just fully normal, right? I look directly down. What do we see? we see this mess. And it's changing every frame because of just the rotation. But this mess is the result of changing just the slightest bit on the camera angle. And so let's go back over. So it turns out I didn't end at chapter 7, I ended at chapter 6. Come on, where are you? Oh, that's chapter 5. Chapter 6. Where are we at? Okay, I remember the wacky waving inflatable arm flailing tube man. Here. Okay, so there's a picture I wanted to bring up to show what the issue actually is. There we go. So we have this line of sight. So the camera has a position and it has a target. And it has that up vector on the camera that you can just kind of, it's just right there. Let me kind of zoom in even to help get, oh wow, super pixelated. So the problem is when you're looking directly down, I think the engine doesn't properly know how to orient that up arrow, or if it does, it's not super consistent throughout the draw command, which is probably why everything just blows up and becomes garbage when you try doing that. So effectively, this camera technique is a good, easy way to get around having to program a whole bunch of transforms for the entire environment. It's conceptually easier to make a game with if you do not allow the player to look directly up or down. Now, having thought about this for about a week or so, I came up with the solution of simply rotating the entire world space every time you get a little bit too close to plus minus Y direction. That would essentially mean once you get a little bit too close to looking directly down or directly up, you just, instead of looking at plus minus Y, you're looking at like plus minus Z or plus minus X, one of the two. Essentially just induce a 90-degree angle situationally that shouldn't affect anything because you'd have to essentially rotate all the draw commands, but not affect any of the mathematics or the physics or anything that you're trying to affect. That should solve that problem. But as SGL tells us, fit width, there we go. The method of just doing moving the viewpoint in line of sight is essentially a redundant viewpoint because it's just adding a little bit of extra overhead to make it easier to program. And it is more efficient just to essentially transform each object individually as needed. And that's generally what I have been doing, precisely because of this issue causing these weird things to happen when you look directly up or down, which I wanted to do for Blue Skies. So I've avoided using this technique. So whenever I make a game, the camera's always facing dead on Z inside a camera space, or screen space, or whatever you want to call it, with the top facing negative Y. And everything else needs to rotate to come into agreement with that picture. Now, having said that, we are done with Chapter 6, as in last time. Now, I will go top off my water, and we will start with Chapter 7 for the evening. Okie dokie. Now, Chapter 7, I unfortunately we're not going to have enough time to go through a lot, so I might only get through like a couple chapters. But I think Chapter 7 and 8 will be very insightful, and probably enough to get you started on making a game if you are following along with me. I recommend you just kind of do this on your own time, but this is a good way of just keeping track for my own benefit, and also some sort of reference I can pull from later. We are going to be playing with face attributes for polygons, and these are going to be presumably textured polygons. So, wow, this thing is kind of annoying. Okay, I'll take it. So, the attribute, so essentially, whenever you generate a texture or set up a texture for drawing, you got a whole list of attributes, and it's essentially 16 bits of flags that you send with the draw command in order to get the thing drawn the way you want. There's this little macro here, defined inside of SGL, that helps you set up things with a lot of enumerated, whatchamacallit, variable names that are kind of descriptive enough to tell you what's going on. So, like, here, let me just go ahead and, like, open up the first example here, and I'll just show you. Main. Polygon. I'll close all this old stuff. So you see this attribute here. We have this. We have a list of attributes that we want to be able to call upon to make our draw commands. And then when we actually do set the draw command, PD plane. So PD plane is itself a P data. So we have a P data that stores, for each quad that you want to draw, you have a P data that holds your point table, essentially the 4 points that make up your the vertices of the quad that you're going to draw, and then your list of quads. In this case, we're only drawing one quad, but it's more or less a description of what the quad is in terms of its vertices. So these are the the indices of the vertices in the point table. So in this case, we're saying the quad is drawn 0, 1, 2, 3, and that's done in this clockwise order. And then the normal, which describes what way the quad is facing. And that becomes useful when we start talking about backface culling or not. Single plane indicates that we are backface culling, which means if the quad is facing us, it's being drawn. If it's facing away from us, it's not being drawn. So that's how you do things like if you're trying to look into a room with your game, the walls are backface culled. So you don't draw the rear of the wall, so that you can look inside of the room. And this is common pretty much anywhere where you have a pretty wide angle camera, or anytime you want to save on draws. Like, say, if you're looking at a box, you only need to draw the faces of the box that are facing outside. You don't need to draw the faces of the box that are facing away from you, because you'd have to look through the box to see them, which you can't do because the box is opaque. Sort center. This indicates the sort order. So it's going to pick 1 point from the plane relative to the camera that tells it what order to draw all the polygons we're sending to draw it. So in this case, Z sort. So all the quads are being sent to SGL's buffer for drawing, and they need to be sorted in draw command in order from nearest to furthest, with using the points as defined by the sort. So you have sort center, sort min, sort max, and I think there's a fourth one that I forget. All right. Texture is just the reference to the texture that you use to draw. So in this case, no texture. We're just drawing a color. And so we define a color using this flag right here. 31 out of 31 red, 31 out of 31 green, and no blue. So red plus green is... Crap, what's red plus green? Yellow? Okay, well, it's apparently drawing yellow. Okay, Gouraud indicates Gouraud shading table address. So in this case, are we using Gouraud? We're not using Gouraud because I'm looking at a different command, or a different example. We're not there yet. Mesh. Okay, mode indicates polygon drawing mode, and there's multiple settings for that. And then let's see, direction, status, polygon, or indicates the status of the polygon and direction. Polygon and texture. What does that mean? SPR polygon. Honestly, I'd have to go look up to see what that means. And then the last one is option. Indicates this is like a catch-all. Hey, you want to do something fancy? Put it in here. What is this? No lyrics on stream. That is not any better. Oh, no, it's instrumental. Never mind. Okay, so let's see. What are they trying to tell us here? Okay, so there's single plane and dual plane. Single plane means we're going to utilize backface culling when we want. Dual plane means we're not. Now, we've already kind of seen what the sample is doing right here. There we go. We have sort min, sort center, sort max, and sort buffer, I guess. In this case, this is more or less saying, okay, whatever order that you sent me the draw commands, that is the order in which I will draw them. There's ways of using that intelligently. Like if you have your own super efficient code for how to draw things, or you know for certain that I want this to draw last no matter what, like a HUD element that's 3D somehow, or something like that, and you can do it that way, and you won't have to worry about putting it at a specific location or specific Z distance from the screen, and have it draw over the environment. Now, the picture for the rest of these is pretty straightforward. Min is closest, center is, weighted center of the average point of the quad, and max is the furthest point. And again, whatever point it uses to sort it out, it's going to go into a table of all the quads you're sending to draw, and it's going to say, okay, whatever is closest to me gets drawn first, sort buffer notwithstanding. So in this case, if I have a quad that I have sort min and then a similar quad at sort max, and they're roughly the same distance away, probably the sort min is going to get drawn more visibly with the sort max getting drawn behind it. So essentially the sort max would get drawn first and the sort min would get drawn afterward on top of it, so that it obscures the one behind it. Okay. So in this case, this explains that the example. So even though this one is like theoretically in front of the other quad, you could set up their sort specifications so that this quad right here would indicate, okay, my max distance is over here, I'm using sort max, so that's the point that I'm using to sort these guys. And this guy, if we're using sort min, the point here kind of edges in front of the maximum point of the previous one. So in fact, this back one right here that you would think would get drawn behind is actually going to get drawn in front, like so. Okay, now texture. Here's the fun part. Oh, we're already at 7.3? Okay, so let's just go look at 7.2, because I think the only thing they really demonstrate in 7.2 is a single quad with backface culling. So in this case, we're rotating a single quad about an axis. When you're seeing it, it's because the texture is facing us and the normal is facing us. When it's pointed away, it's because it's backface culled, and that's because we put single plane as its attribute for how to draw it. Now, texture mapping. So we're actually going to be able to draw textures here. Texture is not going to be used. You specify the macro no texture, but if a texture is going to be used, I imagine we are sending them a texture address. Let's see. Okay. The texture table registered using the function SLInit system. So this is going to be part, I believe, of our work area where we give it some definition. So in this picture that we're using, there should be some form of texture table or what have you, or maybe if it's not here, it might be in the work area. Sprite buffer might be it. Z buffer is a different thing. Honestly, I couldn't tell you which one of these it is exactly. When we get to actually defining the texture, I'll try to do a better job looking for it. But essentially, we're going to, instead of using no texture as a flag, we're going to try and pass through a reference to a texture in order to draw it. Now, this feels a little bit obvious, but only one texture can be applied to one polygon. I guess there is some situation where you'd want to be able to draw multiple textures on a polygon or something. Overlap effects, maybe. There are partial transparencies if the Saturn could do that properly, but, you know, it's the Saturn. Now, what are they trying to tell us here? Okay, so the textures more or less get deformed when applied to the quads. So one texture, one quad. In this case, they have one texture applying to 2 polygons here and getting applied uniformly, more or less UV mapping. The Saturn does not do that natively, so you need to pre-process the textures so they are correctly proportioned to the quads you're going to draw them on. And this becomes especially important when you have non-rectangular quads, or even triangles, in which case you have to predict the deformity. Now, this is why we rely on tools like the ZTP converter, because XL2 has already done the math for us, so we don't have to do it. Now, it gets even worse when we start talking, yeah, like I said, the non-rectangular quads. So they're saying, generally, in a computer system that handles 3D graphics, the way you'd apply this texture is you just effectively crop it to the most sensible way of applying the polygon. Now, in this case, the SEGA Saturn will uniformly map the edges of the texture to the edges of the polygon and just draw proportionally which part of the texture goes in. So in this case, this circle getting drawn onto a non-rectangular polygon will end up getting deformed to look non-circular. Or even worse, or not worse, but like even more obvious, you have a square texture and a rectangular polygon. The square texture gets stretched out on the rectangular polygon. Okay. So they're saying 4x4 matrix type picture. I don't know how much that plays into what I assume it means. However, to note, the width of whatever texture you use to draw needs to be divisible by 8. Not necessarily the height. You can have an 8x1 texture to be drawn. Usually just like a very plain gradient. But you can't have, say, like a 9x1 or a 9x9 or whatever. You can have an 8x9 or a 16x9 or a 24x9 or a 64x9. Okay, anyway, let's move on to sample 7.4. Let's clean up. So I've already worked a few of these samples on my own time, so they're already kind of set up. So here we have a backface called Sonic Sprite, or texture, I guess. Notice how the white background is still there because we haven't defined anything to call it as a transparency. And I don't think it's meant to in this case. So now that we have a texture that's being drawn, let's see what the attribute looks like. We got polygon, we got texture. So here is the literal definition of the Sonic texture. It's just a bunch of bytes. So let's see, what is 16? It's 0 through F that counts for... Crap. I'm trying to figure out how many bytes this is per pixel. So values up to 8 would count toward a byte. But values up to 16 are not 2 bytes. You need values up to 64 to be 2 bytes. 8 by 8. And I believe 64 is FF. Are these 4 bytes per pixel? Is that... I really should know this off the top of my head, and I don't. You know what? Let's cheat. There we go. Let's go to Wolfram and ask it. Hey, Night of Dragon. Welcome to the stream. I already did the announcement during the first 20 minutes or so of the stream if you want to rewind and catch that. Right now, we're just going over SGL samples. And I'm doing some math I shouldn't have to do. I should know this off the top of my head. But FF bits to bytes. That cannot be correct. Let me see. Let's try log 2 of, or sorry, log 8. Six bytes? I'd buy it, but it sounds wrong. So 1 byte is 8. 2 bytes would be 64. This is 2 to the 16. So this is 4 bytes, right? Yeah, screw it. I'm getting caught up on the details I don't need to be caught up. Is what working? So I'm going through the SGL samples. This is not my my CLUT converter that I was doing earlier. That I'll present once it's actually ready to demonstrate. So here's texture data for the AM2 logo. Texture. So here's a texture definition. And then picture. I don't even know what the picture type is. That's new to me. And then picture definition. Sonic and AM2. 32K color. That's a I don't know. He's referred to as a color depth, I guess. It has 32,000 potential colors. 32 times 32 times 32, if I am not mistaken. Times 32 times 32. Each color channel has 32 potential values. Okay, right. So 32 to the third for 3 colors. Going over to Polygon. Let's see. No palette. PN Sonic. PN Sonic is 0 and PN AM2 is 1. So anytime we load a texture, it gets loaded into a buffer that is tracked by SGL for us. I don't know specifically which buffer it is in terms of like if we went back over through common and work area. I assume it's the sprite buffer as defined in work area. In this case, we're saying max polygons plus 6 times 2 is the number. Oh, sorry. 512. So in this case, if it's the sprite buffer, which I assume it is for how we're holding textures, we're allowing ourselves 512 potential sprites to load into memory. You could not see me before? Huh. Weird. Anyway, let's go back to main. So in this case, I've just switched the reference from index 0 for Sonic texture to index 1 for AM2 texture. Okay, so let's see. Gonna be picture. Interesting. Okay, text sample. What's that? So it is a texture. Is that what's defined in here? Oh crap, this is a reference out to this. So at load time, it is loading in specifically the table of textures defined over here. Very interesting. And then we're setting the texture using this function call, and this function texture pointer text sample. Okay, so that is a reference to something we've saved in standard RAM. It's probably gonna be high work RAM somewhere, but not like a specifically mapped portion of it. And then picture is pick sample. Pick sample is of type picture, and it is a table of 2 picture definitions, and then we are selecting No, no, we're not selecting. We are going through the list backwards. So we are setting textures by saying, okay, go through 2 textures, iterate backwards to 0, or to just above 0, I guess. This is a very obtuse loop. Okay, sprite VRAM. That is what we... It's somewhere. You know what? That might be in SGL definitions. So there's sprite buffer, but what's sprite VRAM? Is that defined somewhere specifically that we can refer to? Let's find in all open documents. This is the only reference. So now, I suppose we will go through and check SGL itself. In SGL definition, there's SGL.h and SLDef.h. Let's try SLDef first. Okay. Find what I'm looking for. Find an all. Okay. Define. So this part of RAM is designated sprite VRAM. This is hard-coded in. I mean, obviously we can change it if we wanted to right now, but this is where it's at. OX25C50. Now, I'm sure that's some part of VRAM. Well, it has to be. And it's some part of VDP1 VRAM. Now, how big it is, I don't know how that's defined. Because, okay, 25C, and the next thing to come up is VDP2 VRAM. So it looks like it's somewhere near the end of VDP1. But defined in what way? And this is specifically using SGL's method of loading in sprites, which is essentially using this setup. So they're telling you, hey, the way you're loading sprites here is you're going to load all the sprites you're going to need one time before the program starts, and then play with it. Obviously, that's not scalable. So at some point, what you need to do is you need to set up your own map for the end of VRAM to put in your color palettes, if you're using any sort of color selection method that isn't pure RGB. Of course, these guys are using pure RGB, so they can just take up the whole thing. And partition it the way you need to load in your sprites on demand, so that, let's say you want to go from one level to the next, you don't need to load every sprite in the entire disk in order to proceed with the game. Color mode. Let's just check real quick. Oh, here's the color mode. 32K. And there are other options. I'm currently trying to work on a color lookup table-based approach to make things a little bit easier to get things loaded and running quickly. Okay, now we can actually look at the code part of the thing. So, texture sample. We load in the texture samples. We set the textures in memory. So we're just set texture is essentially writing this hard-coded texture data into VRAM. And that's necessary. And then when we draw PD plane, so here's PD plane, attribute plane, and then the attribute, here's where we actually play with what gets drawn. We change the index, so this is an integer index of whatever texture you want drawn. In this case, we just changed it from the 0 PNM Sonic to PNAM2, 1. And so when we run, Now, instead of Sonic rotating and being back face called, we have AM2 rotating and being back face called. Now, to note, I believe when I was playing with this on my own time, I had to fix the error where the normal was facing the wrong way, making the sprite appear backwards. It was, I believe, facing positive Z when it should have been facing negative Z when it was defined by these vertices. The other way to fix that would be to switch the handedness of these vertices and put this back to positive Z, and that would also have done the job. Anyway, that's about all I think we're going to play with that example for now, so we can scroll down. They explain the transfer the texture data to VRAM, and surely if you wrote your own memory manager, just a way of just tracking what part of VRAM you're playing with, where it's at, how much of it you're using, what's free, you should be able to figure out a way to intelligently load and unload sections of it and just refer to them thusly. Now, the difficult part there, I believe, would be finding a way to refer to them properly in the draw command in order to draw them. Because right now, the way we're building the attribute table here is we give it an index for a texture that's loaded in. And that's handled by, let's see, so this is PNM2, that's just texture information. That's handled by SGL inherently when you're loading in textures using SL in its system. Now, I need to figure out a way to tell it an exact memory address to draw the texture instead. And I'm sure if I disassemble, or not disassemble, but poke through XL2's code, he's got a way of doing it, unless he's also figuring out a way to trick SGL and doing what he wants. Yeah, Phantasy Star 2 actually has a pretty decent soundtrack. Anyway, moving on. SLDMA copy. This is going to be very useful when you write your own loading code, because you're going to want to be able to load in a file into VRAM and upload your own textures and what have you, and color data if you need it. Let's see, texture.c. You know what? Let me take a second look, because maybe I can figure it out. So maybe it's the PicDef. You think the PicDef is what defines this here index, so that you can just arbitrarily use PicDef to do what you want? So let's look it up in our developer's manual reference. Let's look for PicDef. Texture number. There we go. And if I'm using my big boy brain, I can overwrite texture number 0 here. And here, I will send it to point to PN Sonic, which is defined as 0. So we're just calling the 0 basically. We're just saying texture number 0, right? But using my big boy brain, I decided to overwrite the picture definition for Sonic with the picture definition for the AM2 logo. So by calling texture number 0, I should, in fact, produce the AM2, which has overwritten the texture number for Sonic. Oh my goodness! Okay, let's interpret what happened here. Now, keep this image in your brain. We have AM2 on the top, taking up presumably 64 by 32 area, followed by Sonic's head, which is taking up another 62 by 32 area, or 64 by 32 area. The texture for Sonic, the first thing that loads in is a 64 by 64 pixel array. However, let's turn the picture upside down. Let us assume the picture is loaded in backwards. And in fact, if we look through this guy... Well, honestly, I don't know. Let me see if I can, like, use matrix vision and try to figure out what this Sonic picture is supposed to look like. Oh, yeah, no chance. Let's see. Sonic's feet should be mostly white, right? Then again, his overhead area should also be mostly white. Okay, you know what? Let's just assume that I'm correct here, right? So the picture is being written into VRAM essentially backwards, right? So let's say crap. Let's say we have the first bit of the texture being defined as whatchamacallit, the AM2 that is taking up that index there. And that's only 64 by 32. So that's the first bit. Now, what comes after that is Sonic's head. Now, as I load things into the memory, I load up completely Sonic's entire picture. And then, back at index 0, I load in Sonic's head. Now, Sonic's head... Or, sorry, not Sonic's head, the AM2 logo. So the AM2 logo is only half the size of the Sonic sprite, or the Sonic texture. Crap, I'm really stretching my big boy brain here right now, trying to figure out what's going on. Let's look at texture definition. Height. Okay, so this is probably horizontal and vertical, so width and height. They really should come up with better names for that. Pre-size. And the pre-size, presumably, is vertical times horizontal. It's just how many pixels you need to set aside in order to store it. Create the texture for storing. Okay, right. So now, big boy brain time. We have a texture definition of 64 by 64. So it is attempting on texture sample number 0 to draw a 64 by 64. The index that I put for 0 is only 64 by 32. So now it's going to try and grab the next 32 pixels. Where is it going to look for them? Now, presumably, it will continue on to the next block in VRAM and attempt to grab what's there and draw it. Now, the other issue here is texture definition. Now, is texture definition being used in this loading code? Oh, you know what? Okay. Here's how I'm assuming it's happening now. We are drawing essentially at the end of VDP2 RAM, but with an offset or something like that. So I guess we're loading things in backwards. So if we load it in backwards, we put in the entire Sonic sprite, or the Sonic texture. But then we go back to the same index, and then we back out halfway because we're only doing 64 by 32, and then we start drawing the EM2. In that case, if we draw it in paint, we got our first picture, right? This is blue for Sonic, and yeah, this is a solid couple of them. And so here's the first bit of VDP2 RAM that we're drawing in, right? And now we go back and we say, okay, starting from here, but working our way backwards to size it correctly, also draw the AM2 logo, which is half size. So now we're drawing this bit of VDP1 VRAM. So now, when we go back to draw it, what we're seeing is rotate 180 degrees. That. Right? Now, why do we see Sonic's head the right way down? I do not know. The more I think about it, the harder it is for me to come up with the correct picture of what's going on here. I think I've spent enough time on it because I intentionally used the programming correctly. I overwrote the picture definition using the wrong index. And I did it on purpose. Let's go ahead and clean up what we did there. Alright. So we're back to having Sonic in there. So I'm going to have to take a much deeper look into how this code is DMAing directly into sprite VRAM plus texture pointer CG address. Okay, texture pointer. Texture pointer input is texture sample plus the pointer pick sample plus max texture. Okay, texture number. So pick sample comes from here, defines a picture here and here. Yeah, I don't see a very clear answer right here. This is more like banging your head against the table in order to figure out exactly how to handle this if you wanted to customize it. So this is certainly worth the time to explore, but I don't want to waste too much of the stream trying to figure this out because it's definitely an offline figuring out kind of situation. But at the very least, if you're using the SGL framework for just loading everything you need ahead of time, that's the sample, or this sample tells you more or less how you need to do it. Okay, moving on. Okay. Continuing through the tutorial. Let's see. Okay, now we're playing with colors. So you can do solid colors, and then color RGB just gives you the 32 by 32 by 32 color code you need to define the 15-bit color for Saturn texture. Goes from 0 to 31, 32 possible combinations, 32 to the third is 32,768 combinations. We already did that earlier. Okay, Gouraud shading. Just as a Gouraud table for Gouraud shading, Gouraud is a technique that, as opposed to flat shading, which clearly shows the boundaries, like so, smooths things out to make it a little bit less obvious that there are quads separating different parts of your mesh. Okay, so now we are starting to play with Gouraud. So there is this table here where we create 4 different points. So we're taking 6 tables for the 6 faces, and each of them is a table of 4 essentially colors or offsets, and they go do they provide the table here? Where's the table? The table? No? Where's the they had a table or something to show you what you're doing. Okay, I guess not. Okay, so anyway, it goes from more or less minus 15 or minus 16 to 15 or so, and it's the difference between adding colors and subtracting colors. So negative numbers will subtract colors from what you start with. Positive numbers should add colors to what you start with, and 0 should make it unchanged. Now, let's see. Let's actually carefully read this to see what's going on. So there's a Gouraud table, initialization, offsetting angles on the cube so you can see it non-trivially, and then drawing the cube. So this is all stuff we're used to. The routine that draws the cube and rotates is not very different from that is in use before, so explanation is omitted here. Gouraud table is set to VRAM. So in this case, the location in VRAM is wherever the sprite data is, plus, shoot, how big is that? That can't be right. 459 kilo. Really, let's divide it out by 1024. 448 kilobytes. It's a very specific number. Why are we storing at 448 kilobytes ahead of Sprite VRAM? If Sprite VRAM is very close to the beginning of VDP1 VRAM, this would put it very close to the end. Unless it's being stored in VDP2 VRAM, which would come next, I believe. You know, I really should just look at a memory map, huh? Memory. There we go, memory map. Okay, so VDP1 area, VDP2 area, workram area. Can you be more helpful than just that? So high workram. There we go. System variables. There we go, VDP2. So we have sprite command. I don't think we want to touch it. Sprite control command. Plus 6 times 32. Okay, that's for commands, free for users. This is presumably where we can start working with stuff. And it should end here. So, as we recall, the sprite area that we were given was 25C for sprite VRAM. Now, if we add 7 4 zeros to it, we get very close to the end of VP1 VRAM. So we're actually kind of right here. So just near, like I said, just near the end. I'll see, that's where they put it. Gouraud shading table, right before the end. 2 times 4 times 33. So 4 for 4 points per thing, and then I guess 33 tables, and then times 2 for what? 2 bytes per... Yeah, 2 bytes per color. 2 bytes per color, 4 colors, 33 tables. So it's not quite where they put it for this example, but it's in the neighborhood, which is what really counts. So now, I want to figure out how these tables are applied. So is this applied in the same way that the vertices are more or less drawn? So like the points closest to vertex 0 get this one, and then vertex 1 get this one, and then 2, and then 3, but in clockwise order, so it's more like this, and then this below this, and then this left of this, if that makes any sense. Okay, back to what we were reading. Draws a cube and rotates it, etc., etc. Approach is the same as before. Texture transfer. Now all the required tables are first stored in VRAM. So Gouraud tables are stored in VRAM. The VRAM address for the Gouraud table data is stored earlier, specified for the 5th parameter. Interesting. So, Gouraud address. Now, the implications here are that addresses are passable as parameters. In which case, I guess, in the case of Gouraud table, I'm assuming they're passing by reference, but maybe for colors, they can pass by as value, or maybe they'll just pass by reference, I don't know. And then for the textures, perhaps you can send the address that way as well, and just load things willy-nilly in VDP1 VRAM and just send the texture location here and be good to go. And I'll bet you that's somehow how XL2 does it. Now, that's all implications just based off the fact that we're sending addresses over here, but I choose to believe. There, that's... Oh, okay, so there's also offset. So this is not a full address, this is address offset. So this is assuming that Gouraud starts somewhere here. And then we add 1 to each one. And I think this is a shift from this, though. So let's play a little bit here before we read and find out anyway exactly what I'm about to find out. 2, 5, C, 7, 1, 2, 3, 4. Shift to the right 3 times. Hey! There's our E000. So we're assuming this first bit is already just given. It's right there. The E000 is the offset, given that we're shifting right by 3 bytes. And then every time we add by 1, we're adding not... Okay, so we're not shifting right 3... We're shifting right 3 bits in terms of addresses. 3 bits of address is, let's see, 1, and then... Okay. Okay, so first 2, then it's 4, then it's 8. So 8 bytes for a Gouraud table, which is 2 bytes per color times 4 colors for the table. So that tracks. Okay, so then we're starting here, so we're defining it by this offset, and then we go by 1 each time, which will give it the next 3-bit aligned location for the next table. So this will start at 7... Sorry. This will start at OX4B8E000, right over here. And then the next one gets loaded at 4B8E001. Oh, sorry. No. Oh, yeah. 001. And so on, 002, 003, etc., and that's why we can just loop through them like so. In terms of memory offset address, which is distinct from the true memory address, which is a lot longer. Ooh, I love trick track. Cool. Okay. And then parameter must be specified SGL Gouraud. So we're just telling it, hey, we're using Gouraud shading. FYI. Over here. Also turning off the mesh. So these two guys get combined into the same argument, hence the OR. So the OR is essentially just saying, for whatever bits I'm passing through here, if anything is on, then it's on. So if the third bit is on here and the second bit is on here, the third and second bit are going to be on, and the first one's going to stay off. Bitwise OR. Inclusive bitwise OR, essentially. Cool. Okay, no Gouraud. That's kind of goes without saying. I assume that's just a 0 value. I'm sure I could look all these up in SLDef or something like that. Now, mode. What are we sending in for mode? No option. Alright. Yeah, okay. So this is our catch-all kind of mess with stuff. Oh, okay, so we can play with windows. So I'm assuming that we have 6 bytes to play with, and then each one of these guys is going to trigger a byte or something like that. But there's more than 2 values here, so maybe this is 2 bytes, 1 byte, 1 byte, 1 byte, 1, 2, 3, 4, 5, 6. So 3 bytes. And 5 arguments is 3 bytes. So 3 plus 3 is 6, plus 2 is 8, 9, 10, 11. So 11 useful bytes, and I'm sure they can be arranged in different ways or something, but since more or less, this would probably... Either this is going to be... These 11 bits are going to be combined with 5 other bits from previous, which kind of tracks with the attribute being 1, 2, but this is going to be 2 bits already from the arguments. 3, 4... Okay, yeah, I don't think it's going to be... I think what this is this is somehow expanded into a table of 2 bytes per part of the command table, and the whole thing... I mean, this is something I should probably be able to just look up. So let's try that. Command... You know what? This is probably going to be in VDP1 user manual. Command table. Command table, page 25. Not that 25. Come on. 22, 24, 25. Size of the command table is 30 bytes, aligned on 32 byte intervals. Okay, so more than I thought we had. We got our color lookup table, Gouraud shading table. Character pattern table is optional. Command table. 1E. What's 1E? OX 1E. 30. Okay, well, yeah, we were just told that. It's 30. Oh, this includes coordinates and stuff. So the draw command itself is going to be a subset of this. Okay, I've gotten too far in the weeds on that one because we're not even going over that. Anyway, so here's all the different options we can choose. 16 color bank mode, that's something I'm working on. Or, sorry, not color bank, color lookup table. So that you can load in your own little kind of mini palette in VDP1 VRAM and use it to draw stuff, including transparent colors. So this should be useful for saving on VRAM if I manage to fix this up to go with that route. Normal display and display with mesh. That's the mesh in this case is not how I normally use the word mesh, but it's more or less like the not screen door, but like checkerboard pattern for drawing. So that's how they used to do really lazy transparency, where it's essentially just drawing every other pixel. So if you play with it on composite video, it kind of blurs together and makes it look more or less transparent. It looks fine. And if you play on component like I do, it's very distracting. I don't really use Windows. I try to avoid mesh when I can, but I can't always. Let's see what else. Display clear pixels. Do not display clear pixels. I believe this is what I need to set in order to get the transparency to work correctly. Overwrite mode, shadow mode, half bright mode, semi-transparent mode. Now this is interesting. I gotta figure out how to get that to work. And then Gouraud shading mode. And I think these are all meant to be mutually exclusive. So I think if I do this, I'm not gonna be able to do this. So if you have like a half transparent thing, I don't think you can get Gouraud shading. Or you can't get a half transparent shadow. But what do I know? Maybe they're not mutually exclusive. Maybe you can... One option from each group can be specified. Okay, they are. Describe the limiting options with the OR. So you can choose one from each of these. And, like, honestly, just for good practice, you'd probably end up just figuring... Even if you're just using the default, just having one line with all 6 options listed out with the OR symbol will allow you to better keep track of what you're doing and make changes as needed. Okay, dear, this parameter specifies whether the object is polygon or texture, and if it's a texture, how it should be flipped. No flip. Horizontal flip, vertical flip, horizontal and vertical flip. Okay, so you can do a lot of stuff with this. very, very, very quickly and easily, actually. So let's say you got a sprite that's facing to the right, and you want it to face left. Horizontal flip. If you want to turn it upside down, vertical flip. If you want to do both at the same time, you can do that. Very convenient. So that means your sprite sheets don't need to include left-facing sprites if you just want to do right-facing sprites, which is nice. Display polygon. I'm not really sure how that... I mean, polyline, that's just drawing the outline, basically wireframe mode, which is neat, but not generally something I would use, but I'm sure that someone has a use for it somewhere. And then displays a sprite line using the first 2 points. So this is just like a line. So if you just literally wanted to draw a line, you would, I suppose, use the first 2 points of the quad, or the first 2 verts in the table, to define that line. Sure, there's use for that too. It's like a subset of polyline, I guess. Now, display polygon, I believe that means you're literally just drawing a polygon, usually, I guess, as a solid color. Ruh-roh. If a texture is not being applied to an object, do not specify horizontal flip or vertical flip. Specify sprite line with 4 points. Okay, so this doesn't really apply to most use cases, but apparently if you're using a solid color, don't specify horizontal or vertical flip. But if you're using a solid color, what's the point of flipping it? If you're using polyline with a solid color, what's the point of flipping it? So yeah, this is a pretty straightforward. You shouldn't be doing this, but if you do this, don't. Kind of warning. Okay, options. Use light. We've already looked at that before. It's pretty neat. Just kind of brightness, darkness, single white light source. Use clip. Do not display vertices outside the display area. I've not played with that. I don't know what the consequences of playing with that would be. I assume they would make things that get anywhere near close to the edge of the screen just disappear. It's not what I want, so I'll avoid using that. Use palette. Well, this is for polygon color, which again is not something I generally use. I generally have it textured. But if you're having a solid color, I guess you could point it to a palette, and this would probably be like a VDP2 palette from the color bank, from ColorRAM, in VDP2 VRAM. That's above my head. SLDMA copy. Source address, destination against, and count. I'm assuming that's just the size in bytes, but let's SLDMA. Yep, it's how big it is in bytes. So you just take whatever this is and go this many bytes forward and take all that and dump it over here. So if you got something that you loaded into low work RAM and you want to put it in VDP2 VRAM, VDP1 VRAM, that's how you do it. Or I guess in the case of PCMs, you could also try to load stuff up into Sound RAM. Unless something would stop you there, but I don't think it would. At least that's how I make sense of it. Walking Akira Demo C. Let's check that out. I'm going to pull this open up to the side so I can copy over the relevant files, because I don't think I've opened up Akira yet. Actually, where is Akira? Akira. Demo C. Oh, no, this isn't Akira. This is Demo C. Ooh, boy. Okay. Let us maintain all the C files. Delete everything else. Copy over the non-C files that we want. Okay, and then we're going to have to do a few changes. We have to go edit the make file. But we're also going to rename everything to be lowercase to maintain our convention here. Akiwalk.c, akiude.c, akikata.c. Pretty sure these are all just animation files. Akikao.c, akido.c, Aki Ashi Datsi. Oh, actually, no, I think these are components. These are the hand components. Datsi. Okay. Now, in the make file, the sources, we have our main, and then all the Akis. To no longer have Polygon, we have Aki Walk.c, Aki Ashi.c, Aki Do.c, Aki something or another.c. What else we got? Aki Ashi, Aki Do, Aki Cow. Aki Ashi, Aki Do, Aki Cow. Aki Kata. Kata.c. Aki Ude. C. And Aki Walk, I already got that. So, in theory, that's everything I need for the make file. Let's open up all these other files and... So remember, we gotta check a couple things. First, we have to change the main function. We also have to check the end of these files for strange terminating characters that we need to clean up. Of course, they only seem to pop up in main, but I'm checking just in case. There's an H file. I do not recall an H file. Okay, get rid of sub. And then switch main from void ss main to int main. Now, just to be, or just run a quick sanity check on myself. Let me just find the projects. Oh, wait, that's not it. Dang it. Okay. Let's, demo C. Perhaps there is... Because I'm looking through where the, common? No, it's not under common. So in demo C, we don't have any .h files. I don't know what gives. So we got .c's, we don't have .h's. Akira 3. So maybe there's like some other work area. You know what, let's just look for it manually, right? So we're looking for an SS Akira.h, which I do not know even exists, unless it's being defined as such. I'm going to search through here. No items match my search. I don't know how this thing is going... Oh, there we go. There we go. There we go. Include. It's under include. They just packed this into, like, the master suite. What is that? Common, SGL, include, SS Akira. It's just right there. They just say, hey, you're going to need this. Like, in perpetuity. This is just part of this. Like, here it is. Here you go. Why? It's weird. Anyway, warning. Oh, so many warnings. I'm not cleaning up the sample. You spend like all 2 minutes on the sample. Holy crap. Well, that's pretty well articulated. This is a virtual fight. Now, it's doing the walk animation, but there are several animations involved here. Let's see, if I press buttons, does anything happen? Nope, unfortunately not. They have not gone over controller inputs yet. So, we are watching the walking animation. I'm sure if we changed a little bit of code in main.c, we'd find another animation to play with. So this is the Akira, Akira main model demo. So we're going through the SGL. Now let me just close down. So we have animation of a walking human model. The model is virtual fighter Akira. Akira consists of 22 polygon objects. That must be 22 components being drawn, not 22 total polygons, because that is way more than 22. There's no way it's just 22. Each part of a hierarchical structure. Okay. So then each one of these guys is being defined as a subset of the other guy. I don't know why the left thumb and the fingers are components of the arm and not the hand, but whatever. By supplying angle data between each set of parent-child objects, it is possible to create joints. By changing this angle data, it's possible to make Akira move. The angle data between each set of parent-child objects is called motion data. So essentially they're saying, hey, we're animating this thing by moving, let's say, like the hips or the thighs or whatever, and everything attached to that follows, because the lower leg is a child of the thigh, and the foot is a child of the lower leg. So when this moves, we transfer the draw matrix or the transform to the next component. At least this is what I think they're getting at. But one would think that the fingers would articulate relative to the hand. I don't know. They have a motion object. I don't even know what. Oh, okay. No. It's no. It's a defined object. So SGL has like motion programmed into it. Actually, let's see what's in that. No type found. Maybe it's in like Akira.h. You know, while we're here, let's just open up Akira.h and see what's in it. Yep. So they define their own motion file based off of every component of Akira. This is like built into SGL, and you think it's like one of those main components that you can't touch or do anything with, but it's literally just, hey, here's this thing for this this demo we put together for you. We're not going to put it in the actual demo file so you can see the file structure. We're just going to shove it in here, and it's just going to be stuck there unless you think to go and move it. So they made their own struct that's literally just a bunch of angles defining all the relative motions, which is pretty neat. Now they're lighting it. They got a matrix to hold all the matrix data. They got positions, bone length. This is like a full-on articulated skeleton animation on the freaking SEGA Saturn. This must have been a whole lot of trial and error for some artist to figure out how to get done right, because these numbers are pretty precise, and I don't know if they were like defined off of the skeleton model or not. Like, who decided that this needed to be 2627 or 2124? Anyway, so we got Akira position, Akira angle, walk angle. Okay, initialize the system, print out some iterator. You know, it'd be nice if they like put any sort of comments at all into these samples, but okay. I mean, it's not. I don't even know that it's like interpolate. Is it interpolated? I figured they just like put everything on a sine wave and just like calculate based off of delta. Let's see how they actually do this. Jeez, what is this? Comment your code, people. You're breaking my balls. Okay, translating position. Rotate Y, walk angle Y. Okay, so he's like orbiting, right? So the angle is changing and the position is changing probably based off the angle. They're just calculating wherever the location. They're not like doing anything besides just calculating location. They're literally just using a matrix to calculate location and popping it back off. I think I only ever really use matrices to just draw. I don't really use them for calculation. I probably should. But, you know, SL calc point is specifically for that. You have, you know, apply the matrix to these fixed and you get your transform. Okay. So we have a motion pointer, I guess, that is walk I, and I guess, is getting iterated, and then walk is externally defined, probably over here. Holy crap! That is disgusting. Again, so the motion object is triple fixed, and then a whole bunch of angles. Like a whole lot of angles. Okay. Pop the matrix. Translate by the position that we interpolated plus the motion hara position y. Hara position. Okay, remind me. SS Akita hara position. I'm sure that means something. Okay, that's just the fixed component. And these all mean something in Japanese, I'm sure, that I don't know. So this is whatever the offset for the walk cycle is. In this case, starting with a slight Y offset. Y being up-down in camera space. And then we rotate based off of angle. Hara angle is the first angle defined, and it looks like not much of an angle. So it's not like the guy is doing like a front flip or something like that. But yeah, like, so the way that Xenos and I have been doing animations is we just do, like, friggin' keyframes in Blender and just say, okay, here's where the points are, just deal with that. And these guys are, like, doing full-on in-engine skeleton animations, and it's just insane. It's probably, like, a lot more efficient the way they're doing it because of how they're doing things, but then you're kind of limited to, like, the structure of the skeleton. So, like, when Xenos and I make an animation, like, if we want something to, like, blow it up or change shade or wiggle or something like that, we can just do that by changing where the vertices are. But in this case, I don't think you can do that with this without getting, like, really nitty-gritty with scale commands or something. Like, you can't have, like, Akita gain a whole bunch of weight or something and look like a giant blob or whatever, or kind of, like, bend at an odd angle inside of a component, the polygon component. You got like those 22 components, but they're all kind of static within themselves. So his torso is one object. You can't like bend his torso. You can only draw his torso in a certain position relative to the other components. Okay, so we're basically like iterating through every single component down to his cow. I'm sure I should know what cow means. I've been studying Japanese a little bit. I should know what a cow is. Let's go to translate. I'm sure it means like hand or something or finger. Cow. Ah, crap. I should Croatian. Cow. The thing is, I can't like draw it with my mouse. Cow. Oh, no, that's just phonetically. Let's try this way. What's finger? Yubi. Hand. Te. Palm. Thumb. Hand again. Arm. Ude. So, what part are we on? Are we on Ude? Bone length. Mune. Actually, you know what? I should just, like, look at this. Okay, oh, no, they translated it. Crap. I bet Mude is leg. Like, just using my big boy brain logic here. Ashi. Thigh. Lower leg. Hashi. Recognize that. Foot. Torso. Chest. Mune. Okay, so here's his chest. Hara, I'm sure, is like head or something like that. I don't know, let's check. Maybe it's not head. Head? Atama, face, cowl, neck, ubi, hips, hippo, hip, waist. Oh, dang. Okay. I'm sure Hada has to mean something. Maybe it's like master, like position or something like that, or parent body or something like that. Mune was chest, Kao was face, Kubi. Okay, you know what? Now is not Japanese learning time. Okay, but essentially there's parent-child structures all over the place. But the master here is the Hada. But what the heck is the Hada? There, let's ask Google directly. Hada Japanese to English. Okay, I think this is like a holistic job. Stomach. The model starts from his stomach. Neat. Okay, that kind of makes sense from a an animation perspective, and actually the color coding describes exactly that. So maybe I should just like learn to read. So the Hada, the abdomen here, that's the core. And then we get the chest, which, what was that? That was Mune, right? So start with the Hada. We dig down. Mune is the chest. And then on top of that, we also have the Kata. L. Ude L. Okay. So yeah. So I'm sure... based off this picture, we go over the abdomen, we do all the chest and all the children in the chest. So we go down the right shoulder, the left shoulder, go through the neck, the face, the head. And then we go on the other side and do the hips. And that would probably be this bit that I'm talking about here, the left kata, left ude. Ude was arm, right? No? Leg. Ashi thigh, foot, Ashi foot. Okay, well, I'm not going to try and track down every little thing that they were doing, but essentially they're going through that structure in that order. And the more dots that this thing has, the more parent it is, and the fewer dots, the more child it is. And you can just kind of follow the logic from there. Anyway, so that's all the articulation from the animation, and it's imposed by so this is okay, so they do the translation from the bone length in order to anchor the rotation. They take the angles from the motion data, and the motion pointer is set by the frame. Bone count is iterated upon, and then so is... What's MCM count? I'm sure this is probably just like another count for like, here's what part of the body we're on, or something like that, or here's what index that we need to keep track of. So they go through all those iterations for the animation, which is like an insane way of doing animation, but this is like peak programmer brain. This is how we're doing it now because the programmers are the artists too. And then we iterate I for the walk that we're doing in terms of like, this is the frame of the walk cycle. So this whole code is just digging through all this animation hierarchy to make a guy walk on screen. But it is a very impressive model, because you see Akira walk on screen. I do not want to touch a single bit of this code. It is running, and anything I touch would just screw it up. And I effectively feel like I know what I need to know looking at this example. So moving on, let's close all this crap down. It's cool. I don't want to break it. Come on, 7.6. No, not 7.6. Demo C. Let's clean up and move on. honestly, it's starting to get to the point where I need to go focus on other things. And we are at the end of Chapter 7. So it's not quite as far as I wanted to do, but Chapter 8 covers VDP2. So a scroll is a background. So just as a quick introduction, scroll is a background, VDP2 is a background. This is teaching you how to put stuff on VDP2 and use it. And I guess they call it a scroll because you can move them around. So just as a quick, there we go. So more or less, if you want to put text down, you usually put it on a VDP2 layer. 3D graphics go on VDP1, and so do usually sprites. And then there's a background layer you put behind it, and you put it all together, and you get something like this. And it makes sense. And when we have some time, next time, we will go over how to do that. In the meantime, I am going to close down the stream. It was a little bit short, but I've got a lot of stuff to take care of tonight. So thank you everyone for joining me. Once again, emeraldnova.com for all the links to the competition for this year, 28th anniversary SEGA Saturn competition. Learn to make games, make patches for games, make tools for games, and submit them potentially for cash prizes. I will see you all next time, where we will continue by learning how VDP2 works. And I will endeavor to get this stream uploaded within the next few days for posterity. So good night, everyone. I will see you next time.